So today I'm going to change things a little bit. Last time what we did was we were looking at how to estimate the parameters. Now in statistics they call it estimation. In machine learning we call it learning. It's the same thing. How to learn the parameters of a distribution given some training data. So that's kind of like training in machine learning, right? Except that we just have one distribution and we want to estimate the parameters. And we did that for one particular type of distribution called Bernoulli, right? Where we were trying to simulate a toss of a coin. And then at the end of it, I said we can do the same thing for other types of distributions as well. And then I said we can look at something called a multivariate normal distribution, in which every data point is a vector of continuous values. And I wanted to derive it, but you can look at the steps. It's a little more involved. The problem with that one is that since the form, the PDF, is a little more complex mathematically, right? So this is the PDF where you want to find what is the density at value x given these as the parameters, right? So I mean the derivation is a little more involved, but the idea is the same, right? So you compute your likelihood, you maximize it, you apply a posterior, you maximize that to get a map and so on. So I thought I'll actually skip it and maybe briefly talk about it because there's an interesting topic that I want to talk about today so that you are well prepared for the midterm as well, all right? But just briefly, right, the PDF of a multivariate normal. The reason we call it multivariate is because each sample is a vector. There are multiple, so it's a vector of observations. And the PDF, I mean, in general, we write it like this, right? Given mu comma sigma, which are the parameters. And because this is a special distribution, we also write it like this, is written out as just this expression, and you will see this if you choose to follow machine learning, you will see this over and over again because this is one of the most standard assumption that we make with data, that the data is distributed like this, right? So let's look at the quantities. D is the number, D is just the dimensionality, like so x is a vector with d observations. Sigma is the covariance matrix. This is the determinant of that, and mu is the vector, so mean vector. So x minus mu is just another vector, right? So you can, if I give you a lot of data, what you can do is you can compute the the likelihood of the data. So if let's say I have some data which is x1, x2, x3 all the way to xn. I have n data points in my training example. I can compute the likelihood is equal to, and that will just be a product from I equal to 1 through n, and then just this expression, right? So the whole thing, this part, exp, and everything will be same except of course now we are computing it for every I, right? So this is the likelihood, right? And then you can compute the log likelihood by just taking a log, and then this summation product will become a sum. And then what you can do is to find out, you can do the maximum likelihood estimation where you compute the derivative of this with respect to mu and sigma and set it to 0. You will get mu and sigma back, right? So that's a standard way. To compute the derivative, of course, there will be some steps that you might need. So that is the point, that is the time when we make use of things like matrix cookbook. Can tell you what is the derivative of a determinant of a matrix and so on. So those are standard results that you can use. So if you look at the at our handouts, I have the steps there. So I don't want to go through that today. All right, but just to write out the result that we get, at least I can show it here, is that when you do the PDF, right? And when you compute the MLE estimates of mu and sigma, these are the MLE estimates. So this is the mu hat for sigma, for the mean, and that actually looks like just the sample mean, right? So MLE, as I said last time, is it does a very sort of intuitive thing, right? Even in the case of coin tosses, the MLE estimate for theta was just the number of heads divided by total number of trials. So it's a similar thing here. It's just the sample mean. And this you can derive. So those are the steps in the handouts. And the sigma is also just the sample covariance. All right. Actually, this x bar should be mean mu, xi minus mu. So it's just the sample covariance that you get. All right. Then you can also, any questions so far? So this is the MLE estimate. And then you can also say, instead of MLE, as we said, we looked at the black swan paradox, which said that if you only go via MLE, then you are overfitting on the training data, right? You are not using any prior information. So what you can do is you can incorporate a prior on mu and sigma, okay? And then if you want things to be, so we can compute apply some priors both on mu and sigma, and then multiply it with the likelihood to get the posterior and do stuff, right? Now the question is, what priors do we choose? In the case of Bernoulli distribution, we chose a beta prior, and it turned out that it worked well for us because beta is a conjugate prior of Bernoulli distribution, right? So what are the conjugate priors for this MVN? So this is our distribution for the data. So what priors can we put on mu and sigma so that we get that conjugate relationship? The benefit of that is then our math becomes easier, right? So it turns out that the conjugate prior for a normal distribution is a normal distribution itself, okay? So what we do is we put a prior on mu, which looks like this, and then for sigma, now sigma is a matrix, so we want a distribution that samples out matrix, right? That gives us matrix as a sample. It turns out there is a distribution called inverse Wishart distribution, which is a conjugate prior of multivariate normal, all right? So, I mean, I'm just showing this to you. You don't have to go into details here, but when you get time, you can look at it. This also won't be covered in the midterm as well. All right, so that is the idea. And then you can multiply the the likelihood with the prior, and you can get expressions for posterior. Yes, go ahead. Oh, so mu and sigma are two parameters of this Gaussian distribution. Mu kind of denotes, mu is like the mean of this distribution. Where is the distribution centered? And sigma tells you the variance, how much is it spread, right? So these are two different parameters that, and it is a property of this distribution which has two parameters. You can have any other distribution which might have 3 or 4 or 1, right? So that, but here the intuition behind these is that one is the mean, one is the spread. All right. So in fact, I don't think I showed you this particular notebook. But there's one notebook that I typically show in the beginning about probabilistic models. Randomly, right. So, I mean, you can look at it, it's called Random Variables Introduction. And there I have shown you how to use these different distributions. But here, all right. So this is a two-dimensional, these are samples that are being sampled from a two-dimensional multivariate normal distribution. All right, so D is 2 here. And if you look at it, the code here, I am just calling this routine. So this is my distribution. This is already in NumPy. So it takes two parameters, mu and sigma. Mu is a matrix, is a vector which tells you where the data is, and sigma is the covariance. So what I do here is I sample a lot of points and I plot them. All right. Sorry. So when you get a chance, when you go back, you can play around with it, and what will happen is that, so look at this one, right? So my mu is 0, 0, and sigma is 10, 0, 1. So what this says is that since this is a random variable, it can take any value, but it will be centered around 0, 0, right? And then this sigma tells you how much will it be spread along different directions. So for example, if I made it just 1 0 0 1, it will look like a perfect circle. And the reason is that what this sigma is saying is that there is some variance along each dimension, but there is no covariance because the off diagonal values are 0. So you'll get it like this. So if I change my mu, if I make it 10 10, then what you'll see is that now this distribution, this empirical distribution, is centered at 10 10, right? And if I keep changing these values, so instead of 1 0 0 1, if I make variance along one of the dimensions 100, then you will see that this distribution is spread from minus 30 to 50 along that dimension, and only between 6 and 13 in the other one, right? So this is the effect of this mu and sigma on this distribution, right? But what I'm telling you right now is that if I give you this data, I don't tell you what mu and sigma is. How do you compute what mu and sigma is? And what we saw is that for MLE, mu is simply the mean of this data set, all right? So for example, what is this data? This data is this S. S is the data, right? So S is this data. So each example is a two-dimensional random instance, right? So if I just compute the mean of S, so this is the MLE, all right? And what you see is this is pretty close to what the actual value was, right? And then I can also compute the covariance and look. Okay. Ooh, sorry. And then this is the covariance that we have estimated, and it looks pretty close to what we provided. Of course, it's not exact because this is MLE. We're only looking at a sample, right? So this is the idea. Any questions so far? All right, good. So in general, what could happen is that you might get a different form of PDF. And somebody could ask you, how do I estimate these values, the estimates of the parameters given some data? And the recipe is still the same. You take the PDF. If you're doing MLE, you just compute the log likelihood, you maximize it. If you are doing posterior, if you also want to incorporate prior, then you put some prior distribution on your parameters, and then you work with that, all right? So I'm going to stop at that for this particular section, unless there are any questions. All right, very nice. So now let's move to part B3 of this course, which is Bayesian classification. So what we have done so far is we have learned sort of this way of given some training data, learn the parameters, right? But since this is machine learning, what we really want is a way to learn a classifier, right? So remember, we did classification in neural networks, in perceptrons, where I had some training data which had some observations x's and some y's, and then from that I wanted to learn a model so that when I get a new x, I can say what y is, right? So we want to do that, the same thing, but in this sort of statistical manner, all right? So before we jump to that, what we want to understand is that, okay, how does this data get generated, right? So if you remember, okay, so I'm going to change this. Now we move to part B3. Yeah. So if you remember our discussions from a few weeks back, when we used to talk about classification, right? I used to bring this notion of Mother Nature generating data for us, right? So how was data generated was that first Mother Nature would pick up a concept, all right? Then she would pick data, look at the data, look at the concept, and then apply the label to that. So some things would become positive, some negative, and that's how the data would be generated. And then a sample of that would be given to you for training. And your job was to infer or guess what that concept was given this small sample, right? In the case of statistical models, that process is slightly different. So the way that works is that Mother Nature has three distributions, all right? So she has we're talking about two-class classification right now. So that's why there are three distributions. This is a distribution that lets you sample y. Y is the label, all right? So first thing that she does is that she cranks the lever on this distribution and gets a Y, which is the label. So it could be positive or negative, malignant or benign, whatever, right? So she gets a label. Then she looks at the label and uses that label to choose one of these distributions. So these are x given y is equal to whatever 0 and x y is equal to 1. Okay. So based on, of course, if y is 0, she chooses this one and then she samples x out of that. All right. If it is 1, she goes here, samples x out of that. And that way she creates the whole data set. Okay, so this is similar to the data set we have looked before. It has x's and y's, and then what you get is a sample of that, a small sample for training, and then you want to infer what these are. So it's slightly different, and the reason we do that is that once we know all of that, now what you will be given during testing is some x star. All right, and you need to figure out what is the probability that y is 1 given x is x star, and probability y is 0 given x is x star. This is testing phase. And then whichever is higher, you say that is the class, right? And this can be solved easily using a naive Bayes, where we say this is equal to x star given y equal to 1 times the summation, right? So maybe I'll write it out. Right, and this would be similar, except that on the top will be 0, right? So that is sort of the process, right? But the question is, what are these 3 values? Actually, 4 values, right? We need these 4 values, yeah? Of course, this and this are related. This is just 1 minus of this. So what we really need are these 3 values, right? And you can see that all these 3 values can be obtained if we knew this distribution, right? This gives you what is py equal to 1 and py equal to 0. This gives you what is probability of x star given y is 1, and this gives you this y, right? So as long as you have these, you can get that. So the part of training is to look at the data and then estimate the parameters for these 3. So it is very similar to what we did in last few classes, that we would look at some data and we would estimate the parameters for these 3 distributions. However, before that, we have to make a very strategic assumption, which is what distribution do we want to apply here, right? Because it could be anything. Should we apply Bernoulli here? Should we apply Gaussian, Gumbel, whatever, right? So there are so many distributions in our bag of distributions. Which one do we choose? Because once we choose that, after that we know how to estimate the parameters. But choosing that distribution is that bias that we apply here, okay? So there is no systematic way of doing this. We just sort of say, hey, this is what we are going to use, okay? Sometimes the data will determine that for us. For example, we know that y takes 2 values. Bernoulli seems like a good distribution, right? But if y takes k values, then maybe you want to use multinolli or multinomial, right? The same thing here. It depends on what x is. If x is a vector of numbers, right, measurements, then maybe a multivariate normal would be okay. But if x is not a vector of numbers, but a vector of binary observations, then you have to choose something else, right? So that is the key. Choosing the form of p x equal to x star given y equal to whatever, 1 or 0, and py is the 0th step. I'll call it the 0th step, which means that this is not something that you will learn from the data. This is something that you'll assume, okay? And hopefully with experience, we'll know how to do that, okay? So this is sort of the general setting, okay? So now let's look at a specific instantiation of the problem for us. Let's say this is our problem, okay? So this is the same problem we have looked at many weeks ago, where our data is represented using 5 features. Each one of them is binary, okay? So the first feature is either circular or oval, second is large or small, and so on. So 5 features, and our label is just malignant or benign, It's a binary label. Okay, so I'm going to call these x's and this y. So this is our training data. So our training data has this should be n. So we have n data points, x1, x2, x3, and so on. Right. So in the testing time, what we want to figure out is what is y star for a new x star. In neural networks, perceptrons, what we did was we tried to figure out that function. Right. So neural networks is just a functional approximation that connects y and x. But in probabilistic classification, instead, we try to estimate these probabilities. Right? So what we do is, as I said, we apply Bayes' rule. Right? So let's say this is our training data. I've hidden it. The colors indicate the class. But let's say we have 5 training examples. And now we get a new x star. And x star has these 5 values. We want to figure out what is the probability of y to be benign or malignant. So the first thing we can do is we can ignore all of x's, right? We can just look at the y's, okay, and try to do it just as we did in the coin toss example, right? So we have 5 observations, 3 of them are benign, 2 of them are malignant. What is the probability of a new point to be benign or malignant? So you can think of it exactly as we did the coin toss thing, that you get 3 heads or 3 tails, 2 heads. What is the probability of a new head, right? But of course, that is, in that we are ignoring the data altogether. We are not looking at what the values are. We are only looking at the labels, right? But let's say we want to do that, right? We want to do it that way. We want to ignore x altogether. We just want to look at the labels. So we can do it the same way as we did before. We can apply a Bernoulli distribution on that. And then we can estimate the theta looking at these colors only, right? So if you, let's say, and we did that last time, right? So if you just want to go MLE, then theta for this case will just be 2 by 5, right? Because we observed 2 heads out of 5 trials. If you want to apply a beta prior on that with alpha naught, beta naught as the probabilities, as the parameters, then it gets revised like that and so on, right? So we can do that, but that is just a prior for y, okay? So here I'm using prior twice. One is a prior that we apply when we are estimating the parameters, but if we only look at y and ignore x, I call that also as a prior. So this, so you can think of this, right, as just the prior probability that y will be malignant, right? So let's say this is our training data, and let's say we are just doing MLE. So in this case, our y to be head will be 2 by 5, right? And we can be happy with that. So given a new data point, we can say that the probability of the tumor to be malignant is 2 by 5, right? It's a reasonable probability. We are looking at the training data, even though we are not looking at everything inside, right? So that is what we call the prior probability of y to be malignant, right? But of course, then what we want to do is we want to revise it after we observe the data, right? So what we want is, what is y when we have x? And for that, as I showed you earlier, we first want what is the x given y. So this is also known as the class conditional probability for x, right? So this is what we want. So, I mean, this is where you also have to be careful as students as to how to interpret what we want, right? So what we want is, what is the probability of a new data point to be malignant, right? So this, but if I write it out this way, this is not the exact expression. This is telling you what is the probability of x to be whatever you observe, given we know y is malignant. So this is not what we want to compute. This is telling you what is the probability of y to be malignant. This is what we want. What is the probability of y to be malignant given x is this? And we know how to compute it. We compute it by applying the Bayes rule on that, right? So that is the idea. So this is the general sort of the recipe that I showed you earlier as well. Okay. So now comes the question that for this certain example in which we have 5 attributes, what probability distribution should we apply, right? Because we haven't really looked at a probability distribution that generates samples which are 5 a vector of 5 binary variables, right? This is no longer a normal distribution. In a normal distribution, every element in that vector will be a continuous value, but here every element is a binary value, right? If it were only one binary value, then we could have applied Bernoulli to that, right? Because we have seen that, but this is like a multivariate Bernoulli distribution, right? Now the problem here is that now we can in some way apply, come up with a distribution ourselves, right? So if x, our random variable x, belongs to, this is how I write a d-dimensional vector. So if my x is represented as a vector of d zeros or ones, then what form should x take? Right? Now let's look at this, right? So how would we represent this particular distribution, right? So let's say, assume d is 1. If d is 1, that means it's just either 0 or 1. Then we need two probabilities. We need to figure out, in our distribution, we want, because what is a distribution? Distribution is essentially a list of probabilities of all possibilities, right? So we need, what is px equal to 0, and we need px equal to 1, right? And actually these both will sum up to 1. So we need one parameter, which Bernoulli gives you, right? But what if d equal to 2? If d is 2, then what we want is probability of x1 equal to 0 and x2 equal to 0, probability of x1 equal to 1, x2 equal to 0, right? So, and all four should sum up to 1. So actually you need 3 parameters, right? So you can also arrange it in a 2 by 2 table, x0, x1 0 1 and x2 0 1, and you need to fill out that, right? If d is 3, then suddenly you have to take care of 3 possibilities, right? So that means that you have to have 8. Yes, go ahead. Yeah, so I'm coming to that. So right now what we are saying is we are not making any assumptions about dependence or independence of these variables, which means we will have to list out all possibilities. But, and that's sort of the next point I'm going to make. So the question was, what if some of these x1, x2s are independent, which means that this is nothing but just the product of these two? Then you don't have to compute all of these, right? Which will make it easier. And that's actually what we will do in the next step. But right now, let's assume that there is no independence. So now here, we will have to write out 8 combinations, right? And then they have to sum up to 1. So it will be 7 parameters. So in general, when d is d, you actually need 2 power d minus 1 parameter. All right? So those are the number of parameters. Oh, actually, and then you have to do this for each class. Remember, we want to compute this and this, right? 2 distributions, which means that we have to compute this for both classes. So it will be, so for 2 classes, this will be 2 times 1, 2 times 3, 2 times 7, 2 times 2d minus 1, right? Lot of parameters. So if your d becomes suddenly 10, then you're looking at hundreds of parameters in your distribution that you need to estimate, right? Now the problem with that is that if you remember coin tossing, right? So when we have coin tossing, we only need to estimate one parameter, right? So but we at least need 2 tosses to get some reasonable data, right? So if I toss a coin once, I get either heads or tails. We do not have enough data to estimate the theta for that, right? So we need to toss it a few times. The same thing, let's say if I have a dice which has 6 faces and I want to estimate the probability of coming phase 1, phase 2 through phase 6, I need to roll it a few times before I get some reasonable number. Yes, go ahead. What is the parameters? Do you mean x1 and x2 are parameters, or do you mean you have to compute? Right, it's a good question. So x1, x2 are the features, right? The parameters are of this probability distribution, right? Now remember that this is a discrete distribution. It only takes a finite number of values. So the parameters are the probability of each possibility, right? So if it's a coin, then we have only one parameter, which is probability of heads. But if it is a dice, then we actually need probability of phase to be 1, phase to be 2, phase to be 3. So those are the parameters. Oh, so in this case, how many possibilities can this random variable take, right? It can take, both can be 0, both can be 1, one can be 0 and other is 1, and so on. So there are 4 possibilities. So you need 4 parameters, 4 probability values, but they all sum up to 1 because those are all, so one of them is sort of dependent on everything else, right? So the same logic will apply to any general case. But the point I was trying to make was that if you have more parameters, you need more data to estimate those parameters, all right? Which means that if you have so many parameters, you will need a large amount of data, because otherwise what will happen is that if you have small amount of data, then a lot of these possibilities might not occur at all, right? So if you have a 12-sided dice, right, and if you roll it just 10 times, then you can be certain that some of the faces will not be observed at all. So that means that if you just do MLE, then you would their estimate would be 0, okay, because you have never seen it. You can apply some prior on that, but then you're not really learning from the data. So which means that you need lot of rolls of that dice, right? Lot of work to do that. The same thing applies in general settings. So if you have lot of parameters to estimate, you need lot of data. So it's kind of connected to the VC dimension as well, right? So if it is more complex, then you need more data to learn things reliably. So what do we do now, right? So that is a problem, of course. So what is the problem? The problem is more parameters implies more data, and data is not easy to get. So what do we do, right? So one thing, as you had pointed out, is that what we can do is we can simplify the form of this distribution a little bit. So for example, if we assume that all of these things are independent of each other, right? So let's see, how do we reduce the number of parameters? So let's go back to this one, right? Assume that x1 and x2, these are the two, let's say our d is 2, are independent. So what does independence mean is that the joint probability, so p x1 equal to 0, is just the product of the individual probability, right? Which means that instead of, so if I want to compute these 4 numbers, wish I had a copy paste capability in this pen. So this would just be this, right? So this will be px1 equal to 0 times px2 equal to 0. This one will be px1 equal to 1 times px2 equal to 0. x2 equal to 1, right? Any questions about this part? This is just assuming they are independent, which means that to compute all these values, we actually just need 2 values. We just need, we need 4 values. This, and this, right? So we need 4 values, and actually these would be connected, right? So if I know what is px1 equal to 0, I already know what is px1 equal to 1. So I actually just need 2 values. As long as I have what is p, all I need is px1 equal to 1 and px2 equal to 1. Right? So suddenly, instead of trying to figure out 3 parameters, I just need 2. So I have reduced it. But what you will see, now this doesn't seem too much, right? But when you go here, when you're looking at a general case, then when you make this conditional independence, you significantly reduce the number of parameters that you need. Okay? And what that will give you is that you do not have too much data. So with conditional or not conditional, I'm sorry, with independence assumption, right? What happens is that the number of parameters that you need to express your probability distribution for x reduces significantly, and because of that, we can learn even with less amount of data. So that is the principle, right? However, the thing that we are losing here is that we are making a pretty strong assumption. We are saying that these different variables are independent of each other, which in many cases might not be applicable, but we still go ahead with it. All right. So this is a model that we call naive Bayes classifier. All right. So naive Bayes classifier is a probabilistic classifier which makes the assumption of independence. All right. So that the number of parameters that it needs to estimate is smaller, and then it works with that. All right. So naive Bayes classifier, sometimes I'll also call it NBC, which is the main acronym. Okay. So the next question is, any questions about this? It's fairly straightforward, right? So then the idea is that, okay, what do we do now, right? So essentially, so this is sort of the graphical representation of this model. Yes, go ahead. How do we need 3 parameters for the original setting? So let's see here. All right. So you mean for this, right? Before the independence. So see, what we want to figure out is we have a random variable. Okay. So we have a random variable x, all right? X has 2 things inside, x1 and x2, right? So this is my random variable. Now, how many values can this random variable take? This is a discrete random variable, right? So how many values do you, and each one of them is binary. So you can take 4 values, right? So it could be 0, 0, 0, 1, 1, 0, 1, 1. When we try to estimate a probability distribution for this random variable, what we need to compute is what is the probability of each one of these possibilities, right? So we need, what is the probability of this to happen, this to happen, this to happen, this to happen. So we need 4 probabilities, right? However, since these are the only 4 possibilities, that means by just the basic law of probability, all of them have to sum up to 1, right? Which means that we just need 3, the 4th one will be obvious. So we need those 3 probabilities. So I call those as the parameters, right? Any other questions? Okay. So, right, I was looking at this. So what we are assuming in the case of naive Bayes classifier is, we call it naive because it's making this very naive assumption that everything is independent. But it works pretty well in real life. A lot of people use it, so it's not that naive at all. So the idea is that you have D features, right? Each one of them is binary, right? In naive Bayes, each one of them can actually take more than 1 as well, or more than 2 as well. But so right now we are assuming each one of them is binary. And Y is what we want to predict, right? So they are connected to Y like this. This is also known as a probabilistic graphical model, where we basically, the edges encode the dependency, all right? So here what we are assuming is that all of these random variables are independent of each other because they are not connected to each other. But they, of course, Y depends on them, right? That's what we are computing. And all of these sort of connected to these. So they are, I mean, you can think of these as not truly being independent of each other because there is some path from one to another, right? If you know one, then it's not like the other one's probability won't be high, right? So for example, let's say, all the malignant tumors are dark red and big, right? Now you see a tumor which is dark red, then you can, it's not that you cannot make any judgments about this, the size, right? You can You know that if y, we don't know what y is, right? But you can, because there would be some correlation. Whenever there is a dark red tumor, there's a good probability it will be large if y was malignant, right? So which means that they're not truly independent. The reason we call it independent is once we know why, then they are independent. Okay, so that's why we also call them conditionally independent. Given why, they are independent. All right. So that is the notion, the discussion of conditional independence we had last week. So refer back to that. But the idea is that all of these features are independent of each other given why. Right. So what happens because of that assumption is that now we suddenly need only 2 times d parameters, because you have d variables, right? Each one of them is binary, which means that each needs only one parameter, right? You can think of each one of them as a coin which you need to toss. So you need to estimate the parameter for each one of them. And then there are 2 classes. So for each class, we need these parameters. So you need 2d parameters. So suddenly from 2 times 2 to the power d minus 1, you just need 2 times d, right? So significant cut down. And because of that, you can learn with less amount of data. Any questions so far? So that is sort of the setting of naive-Bayes classification. Now let's just quickly look at how do we estimate the parameters, because eventually what we want to do is, we want to do this, right? We want to do, how do we compute that? So the first thing that we note is that because of this naive-Bayes assumption, what has happened is that the probability of x to be x star, right? Now x star is a vector, the whole thing, given any class, let's say y equal to 1, can now be written as a product of I'm really careless with my notation, but all right. So this is the key assumption that we are making. We are saying that given the class, right, we are assuming that the joint distribution of x, because x is a vector, right? So when we say this, all we are saying is what is the joint distribution of x to be x1 star, which is the value of the first feature, times comma value of the second feature. So all of that can be just written as a product of these, right? So that is the independence assumption, right? So now the problem reduces to how do we compute these values. So this xj is the jth feature, or x star j is the jth feature in the x star j vector, in the x star vector, right? So now we need to compute this, and of course we had to compute the prior on y, right? So this and these. If we can do that, that's it. Now we can apply our naive Bayes and get a probability for every new instance, which are these. All right? Any questions so far? All right. Okay. Right. So I don't know why I write this. Okay. So now how do we find the parameters of those distributions, right? Because now we have little distributions hiding in this giant expression, which are here, right? So we have d distributions that we need to estimate the parameters for, and we had one prior distribution as well. So to compute the parameters of the distribution, what we do is we take our training data, right, and then we just compute the likelihood and compute the maximum likelihood estimates. Or we can apply some prior on those distributions if you want map estimates, or if you want to do Bayesian classification, you can do all of that. But let's look at it purely from the sort of the MLE estimate, right? So we want to find the parameters that maximize the likelihood of our training data. So the first thing is, what is our data, right? So here, our data is not just x's. Our data is x and y, right? So now what we do is we compute the distribution for x comma y. So we have x, which has d binary features, and we put a comma y, another binary feature, and we assume all of them are independent of each other, right? That's the beauty of this. which means that the joint distribution can just be factored as a product of these. The probability of y, the theta are the parameters that we will compute now, y, and the probability of each feature inside x given y. All right. So once we have that, we can compute this. We can compute the likelihood, log likelihood, and then set the derivative to 0 and compute the theta. All right. So this is the slide that when you go back, you want to look at a little carefully, right? So the parameters that we have are, what is the parameter for y, because we want py, right? And then the parameters, we also need the parameters for the benign class and the malignant class. So we have two classes, theta 1 and theta 2. So we want to compute theta 1, theta 2, theta. All right. So, and the distribution looks like this. So all we do is we compute the likelihood of the theta, likelihood of the data with respect to theta, which is just the product over all of your data. All right. And then we compute the log likelihood and maximize it and so on. So we will do that in the next class. But here, all I want you to sort of remember is what we are doing here, right? So let's look at this expression. Out of time. Well, maybe we'll start the next class. I just have a minute. Any questions that you have? So remember that this portion will be in the exam. So make sure that you are familiar with this. It's pretty intuitive. All right. So it's not something that if you spend some time you won't get. All right. No more questions. So I'll see you on Wednesday. Oh, there was an announcement, right? I don't have my office hours today. I have a meeting after this. So what I've done is I'll have office hours on Wednesday, same time, 10 to 12. If you do not have time then just send me an email. We'll set up a time to talk.